Good point. What? You get it? How'd you do it? X is connected to E, 16 watts dissipated in X. Y's got the same material, the same diameter, but twice as long. What is that going to do with the resistance if you increase the length by a factor of 2? What does it do to resistance? Eric?
Increase it
By what?
by a factor of 2.
By a factor of 2. So we've doubled the EMF, we've doubled the length of this, so we've doubled the resistance. Alright? Both cells have no internal resistance. What power is dissipated in Y? So which equation might we use for this one as a starter? Taylor?
P equals VI.
Which one?
P equals
P equals
VI.
VI. Would you use that one? This is quite interesting actually. We've doubled the resistance, right? No, you may be right. This one is interesting because look, we've doubled the resistance, do you agree? Because we've doubled the length, and that comes from the resistivity equation. And the resistivity equation is R equals rho L over A. So if L goes to 2L, then R goes to 2R. Now if that's the case, we've doubled the resistance, but we've doubled the EMF. Agreed? So if we've doubled the EMF and we've doubled the resistance, what happens to the current, Jay? What does the current do? What's the current do? Hannah? No. What have you done to the current if you've doubled the EMF and you've doubled the resistance? There's no change in current, absolutely. So what we've got a situation here where I equals E over R, or 2E over 2R, sorry, my writing's a bit off, so it's the same, right? So there's no difference. If the current is the same, then it tells us that we can calculate the power dissipation. So the power in X is I squared X. Well, sorry, inaccurate Rx, well the power in Y is R squared 2 Rx, because we've doubled the resistance. Get it? So it must be 2px, because px is I squared Rx. And I squared Rx is here, the 2 is in front. So there you go, we've doubled it up. So what is the new power, Jay? What's the new power in the question? Was 16, right? What is it? 32. Right. You follow that one, guys? Well, actually, I think the secret to this is to look carefully at every piece of information that is presented and looks different, and then look at where they're stating that things are remaining the same. And you will obviously be referring to a specific equation here. You pull that in from the equation booklet, and then the whole thing falls together, as long as you pay attention to every single point that is made here. Now, I would probably circle the 16 there. Or if you circle all the data, you know you have to use it, right? So, and then we look down here and we look at anything like same, twice. These are all key terms as the variables that are changing or not changing. 2E rather than E. That sets you up. So let's try on the next one, see if we can do it on the next one. Once you start thinking this way, your success rate rockets. Now, how if you don't read and study beforehand, then it's going to be problematic. But I had one student many years ago said, if you talk about solution strategies and how to solve problems, that was the most useful thing I experienced, is how to read a question and work with it. And that takes time and it takes effort. But practice makes perfect. So it goes with my philosophy that the students should always be solving problems, because if they're not engaged with the material. It's really important that you're mentally engaged with the material as often as possible in the lessons to get max value. So if you go home and don't do much, you've still done some solid physics that day, 4 or 5 days a week. So what we're looking at here is regular application of mind in physics, so that you develop throughout the whole course. Right, let's have a look. Evan, any luck on number 3? The actual answer is be on number 3. Can you read it? I think this question is brutal, actually.
I got this one wrong.
You get it wrong. Anybody get this right? Daniel, do you get it? This is really, really unpleasant question because we've got these. We've got 3 different powers dissipated, or 2 actually, 10, 20, and 20. And what's strange about Y and Z is what is the current they get from this circuit in relation to X? What happens to the current as it goes down here? Because it's actually telling you that these 2 are the same. X and Y, in fact, the same power rating. So what is it telling you about the current?
It halves.
It halves, right. So what I did on this one is I thought, okay, the power of X would be I squared the resistance of X, yes? I don't know what it is, I don't mind. But the power in Y would be I over 2 squared RY. And it tells us that the power dissipated is 10, 20, 20, which is really good. So it allows us to actually state already what's going on. And that should give you enough to find the resistance ratio for these 2 resistors. All right? And then you can start working with voltages. So what is the resistance ratio? Any idea? What's the relationship between Rx and Ry? I'm not saying this is the best way to do it, it's the way I approach it. Yeah? What's the relationship between Rx and Ry? What's that ratio? Do you agree with that? Yes, I brought the 2 squared up to the top. I squared's gone. I brought the 2 up to the top there in front of Rx. So in this particular case, Rx equals 1/2, in fact 1/8 Ry. So in fact, X is quite a lot less in resistance than Y. Does that allow you to get at the question now? Can you get at it now? We can redraw it, okay? We can draw it in a slightly different manner, and that is by using just pick some numbers. We said Rx is an 1/8 Ry. So if Ry is 8, then this must be 1 ohm, right? And that's 8 ohms. So I'm just making some numbers up now, which is another strategy you can use, right? So if we just pick Rx or Ry as 1, it doesn't really matter. We can do that if we